for now. So please, if you haven't filled in the survey, please fill in the survey. Okay, the survey is there is so both classes combined. It's only um, 67. So a lot of you didn't fill in the survey. I've put the link on the Google Classroom. I've also put the link on the Google, no, the Moodle. But it seems that you didn't fill in the survey. I'm not sure who hasn't filled in, but please make sure and tell your friend to fill in the survey. I will make the announcement for the final exam based on that survey. And for now, since we have 67 students from 2 classes combined together, we have, I think the most suitable time is Saturday. The pop quizzes is actually will be combining all together. Will be we have the normal quiz, right? The small pop quiz is combining together. If you look at your wait a minute, I need to share my screen. So the small pop quiz, combining all together, it will be equal to the so you have first, sorry. So you have the quiz, right? You have the midterm. You have the final. So the small pop quiz is put here. So I think this is 30, right? 20. And maybe this is around 20 to 25, right? If I'm not mistaken. And the rest will be your TA and attendance. TA and attendance, if I'm not mistaken. I will probably announce this also in the Google Classroom about the percentage of all of this. So the small pop quiz will be contribute to this quiz. So we have so far quiz 1, quiz 2, right? The first chapter, and then quiz 3, and then the last part is the pop quiz, right? I'm planning to have another pop quiz this week, but I think I will cancel off that. I will focus on finishing all the chapters, maybe giving you another homeworks for the chapter 15. And I hope Thursday, on the Thursday class, we can have some exercise, especially for chapter 15, because I think the most difficult one is the chapter 15. Okay. Okay, I can now going forward to a little bit review from the last session. The last session is having this. So if you read your textbook, okay, you will learn that you will have. So first, to generate these triple integrals, okay, over general regions, you have 2 components. Okay, you have 2 components. First is the solid E, which is your solid here. Okay, and this E will have upper and lower boundary. Okay, and it will be a function of double or a function of 2 variables. In this case, in this picture, it's xy, right? Another element is the region D. This region D, you can treat this region as a double integral, okay, in which we have learned from previous sections. In this case, we can treat this, we have this is the delta x and delta y, right? If you have defined this into a rectangle, and we can define the rectangle into a double integral. And thus, this E, okay, this E, we can split this double integral becomes D, okay? And this integral here, the inside integrations will be having upper and lower boundary from the functions of the surface, okay? The surface here, okay? And now, because of that, we can now see at least, okay, this is type 1 solid region. So this is type 1. So there will be type 2, right? And also type 3. That depend on how the volume will looks like. So the type 1 is having z equal functions of xy, right? For the surface. Type 2 and type 3 will have this kind of surface and this kind of surface. So this will be functions x and z. This is y and z. Okay. And what I'm going to refer on all of this is type 1, type 2, and type 3 is not important. Okay, not important. I think if you just read the textbook, you will realize this type 1, type 2, type 3 is not important. Why? Because if you can just see the picture or maybe see the functions like this, you can set up the functions and set up the integration. So when you have this xy here, you can develop this, right? You can develop this xy. So you will have z here, and this will be, it's either function of y or function of x, depends on the cases. But if you have the function of x, this should be y. And then lastly, the x will be the constant and x. Okay. And if you have function of y, you can change this into y, and then this will be a constant at y, right? So you can also have yz or xz. Okay. So for example, if you have yz right here, so this should be the x at the very beginning here. And the rest, it could be dy dz or dz dy. Okay, so I hope you get the logic behind how to make up the triple integral. Okay, this type 1, type 2, type 3, like in this double region, also a double integral also have type 1 and type 2. It's not really important as long as you know which one is the functions and which one is the constant. Okay, okay, I think that's the idea behind the triple integrals. Okay, I will give you an example. So you have E, you have, okay, you have this general equations for triple integrals. E is bounded by, okay, we have this surface, a paraboloid, of course, and then a plane y equal 4. Okay, now if you want to take a look, because it's not that complicated, we can draw the paraboloid to show you what does it mean for these questions. So let's say that is our circle. Let's say our circle is at equal 4 based on this. And let's say this is the 4. So this is the plane here. So let me make another circle here and make the parabola. This is the first parabola. Okay, so you have the paraboloid like this, and then this is D. D is actually our circle. The projection's D, right? So we can set up these two equations that we can follow. You can choose which one. You can just Z or X, and it will determine our integrals. So you have triple integrals now. Write the x squared plus z squared. Okay. Because you know the boundary is y equal x squared plus z squared. So it's better using this into the first integration inside, right? So we can set up this as dy, okay, from x squared plus z squared until 4, right, for this y. For the second integrations, I will set up z. So I will put this information. So I will have, let me write this. And then the rest is x. The last one is x. This will be 2 and -2, right? The radius is 2. So it will be -2 to +2. Okay, first, let's just try the first step to integrate the inside, okay? It seems complicated, but let's try to check it first. So let me write -2. Okay. And then try to integrate it to become y, right? Y squared plus z squared. And you need to plug in x squared plus z squared and 4. And I can now write this into 4 minus x squared. Let me write like that. Make a bracket to make all the calculations to be carefully be approached. So we will have this is still having the z, the x, and then having these two double integrals, -2 to. Okay, now we have this set up. Okay, the next thing is if you are trying to solve this, you will be really difficult because you have this and this, right? How to integrate those. So the idea now is to convert to polar. This is the way that you can simplify the equations. Now look at the circle here. If you want to convert to polar, we need to know the angle. I believe all the circle will be evaluated, so we need to take 0 to 2 pi. And the radius is from 0 to 2. There is no other radius, right? And then we can convert the theta and radius And this was the definition here. The circle is x squared plus z squared, right? So we can set up 4 minus r squared. And r squared here becomes r. And then multiply with r dr d theta. We can set up the d theta here, and the rest will be and then we can compute. And then this is around, and then you can try to find the answer. Okay? At least this is the way to answer. So in triple integrals, you can actually convert the polar to solve the solutions. And I think based on your exercise that I have given to you, the homework, see some of the answers, but I think some of you still having problem with the volume, the subtraction of volume. Uh, the way you look at, okay, if you have double integral, you have some constant from here to maybe this is -1 to 1, okay, and you are given the subtraction. So you are given maybe z is 3y and z is the other z is 2 plus y. We need to know which one is the highest, the first one or the second one. How to know that? We need to know from how much value of y that is being evaluated. If this is from maybe -1 to 1, then we can evaluate, let's check 0. When y is 0, the this z is 0, but this z is 2. So of course, 2 plus y is above the 3y. So we can set up 2 plus y minus 3y. But it also depends on the case of the interval. Okay. So you need to evaluate based on the interval that are being evaluated. Okay. I need to move on to another sections, which is the cylindrical coordinates. Okay. So there is application integrals for the sections, like the mass in a moment inertia, right? I'll skip that for now. We don't really need to compute that. We just focus on the calculus problem. That is more likely to be physics, so I will skip that. So the next section is triple integrals in cylindrical. Okay, now the cylindrical, the cylinders, if you remember, if you have x squared plus y squared equals something, and you have z, some constant, you will get the cylindrical shape, right? If this is on the origin, the circle, so probably you will have a cylindrical. So it's going up and going down like that. And now we are going to use this form to make a standard. Okay. So we will have let's say this is, we have r here. Let's say this is the radius of the polar. Okay, and this will be the theta. And then you have some z for the surface level. Okay, let's say this is becoming some point here. So we can say that at this point P, the coordinates, aside from saying this x, y, z, we can also write down in terms of r, theta, and z. R and theta refer to the radius and the angle that in the polar sections on the plane. Z is for the height. Okay. And to convert all of this, like to make it into the x, we can convert through these relations that you're already familiar with. Okay. And then to evaluate the triple integrals, recall this LMN, and you have triple integrals LMN from I equal 1, j equal 1, k equal 1. And then you have ijk, yijk, and zijk. And then delta volume. And delta volume is area multiplied by height. And remember, in the polar, in the 15.3, the area is r, ri, and then delta ri, and then delta theta, right? And the height will be the delta z. Now we are going to set up the similar approach to our cylindrical coordinates. Okay. Do I have the picture? Let me check the picture first. Okay, maybe I will draw first. If you remember, if you have a solid E, maybe this is a solid E, okay? And then you have projections here. And based on these projections, let's make the projections become a polar. So let's set up the projections and take that into a polar. So it will start from wait. Maybe here is the theta equal alpha. And then, wait. And then this will be maybe different color. maybe here is theta equal beta. Okay. And then we have 2r. This is r. Let's say this is a function of h. And this the r1 is r2. R1 is here. Maybe there. Okay. Now we can set up similar to what we have did in previous triple integrals. We can set up this polar on the xy plane like that, and then we can also set up the triple integrals. So let's say this is d, and we can set up this as our double functions of two variables. So let's say this is u2, and let's say this is u1. Okay. And then set up the integral here. And this is the functions, the total functions. And this will be dz dA, right? And the rest, this dA and this d, we can convert into polar. So it's actually what we did on the last example. So this will be, or let me write in more details here. So you can convert this into, this is the theta, this is the r. Let's say the r is a functions. And the last one is, you can write directly change to all the polar to make it all polar. So x will be r cos theta and y will be r sin theta. And then this is f, and then we can write r cos theta for x, r sin theta, and z. And this will be r dz dr d theta. Wait, let me move here. Okay. I hope you get the point. Okay. So the idea is just the same as usual. So determine the surface, determine upper and lower surface, and then take this 2D sketch and then take it into a polar bounds for r and theta. Okay. Okay. Let's see if you can look this. So if you have this let's say you have this okay, if you want to set up into cylindrical, you can set up by looking at these two first. So this is x, first one. Second one is y, right? based on this integrations. So we can look up here that this is 4, 4. Okay, to make it clear, okay. Not y. So you have y plus minus 4 minus x squared. Or you can write this is a circle equation with radius is 2, right? So radius is 2. And because we are evaluating from negative to positive, so we are evaluating on the whole circle. So 0 to pi, and then 0 to 2. And then we can set up the cylindrical. So change this into R, right? And the constant still same constant. It's z. Z is always z. Not, we are not really changing z, right? And then x squared become r squared r, and then dz, dr, d theta, and then you can solve this. Right? Okay, another example. Maybe last example for this one. E can be a region inside a sphere with radius is equal to centered at origin and above plane z equal 1. So find volume of this E. Okay, I think we can draw the sphere. Not really that difficult, right? It's not a complicated or difficult surface. Let's say this is the circle in the middle. So this will be let's just make around. Okay, let's just make that is our circle. Okay, and let's say that it has r equal to, and then it has plane z equal 1. So let's say this is z is here, z equal 1. So maybe z equal 1 is here. So the blue one here will be our E, right? This is E, okay? And then maybe we can write down the sphere. The sphere is x squared plus y squared plus z squared is equal to. Maybe remember that it's also the same, similar to ellipsoid. The difference is all the constant, all the same for a sphere, right? And oh wait, not 2, 4. Sorry. It's r squared. And z is equal 1. So that we can also make this into our z plus minus 4 minus x squared minus y squared. Okay. And then we can also start to look at the radius, right? So the radius will be changed, right? Or there will be a gap because of the z equal 1, right? So z equal 1, when you try to put z equal 1 into the equations, it will make the equations becomes x squared. So you can see here, you can make this equal 3. Which is now you have the r is square root of 3. So this is square root of 3, right? Okay. And then we can set up the triple integrals. This is can be 4 minus r squared for z, right? So the whole circle is 0 to pi. And the circle at this green one is square root of 3, right? And z is from 1. Okay. Look here, it's from 1 here, from 1 to this, right? This is the 4 minus r squared. Okay, so we can put in 1 and then 4 minus r squared. And then the equations become r dz dr d theta. Okay. So actually there's no other functions, right? So actually this is just an empty equation. So you need just to evaluate the boundary, and that is becoming our volume. And integrate all with r, with z, with r, and with theta. Okay. Okay. I hope these two type of uh, examples can be helpful for cylindrical coordinates. Okay. Mm, another sections on the um, this chapter 15 is about maybe new sections. It's 15.8. Okay, 15.8. So this is triple integrals. In spherical coordinates. Okay, now this is quite a little bit complicated. Okay, maybe I can explain through the picture here. Um, okay, maybe before we're going through here, let me draw this simple a simple picture for you. Let's say we have this is the radius, okay, and we have the angle theta here. So this is the radius, and then we have okay, this is point P, and aside from the theta, we have another angle. We have another angle, psi angle. Okay, let's say in that from this C. And we can set up the point P here in terms of this length here, the light blue here is rho. The coordinates for point P is rho, and then theta, and then psi. Rho is always positive, and theta is between 0 and 2 pi, and psi is just 0 until pi. So this psi is only up until here. Okay. Okay. If rho is a constant, it will be a sphere, right? It will be a sphere. Okay. Imagine it has the same amount of radius, so the radius rho there. If the theta is a constant, it will be a plane, right? A plane like that. If you look at the plane like that, right? If the psi is a constant, it will be a half cone. So it will be half cone like that, like this. Okay, can you imagine that? Okay. Okay. Now, if we want to look into more details between the theta, let me mark this to blue, the theta, and then psi here, and this is rho. We can actually imagine there is our some small rectangle like this one, small volume of rectangular shape. Okay, and based on um, the angle, we can convert the radius into rho, this radius here, right? And then this becoming rho sine and delta theta. And this will be rho and delta theta from here. Okay. This is the approach to see the volume of the spherical coordinates. Maybe I will, or maybe I will write here. So let me write all the correlations. So this is the first time we learn, right? This is r cos theta, y is r sine theta. And then R here, let me check here from here. Okay, let me make another line to help to design what we are doing here. So this is the line. Let's say this is y, this is x. Okay, and then let's say this is z. Okay, and this is also psi, right? The same angle, right? So let's look at this triangle, rho, z, and r. Okay, let me make another angle here. Okay. Okay. Okay, let's say this is this psi. Oh, wait, rho. This is rho, this is r, this is z. Okay. Z is rho cosine psi, right? And R is rho sine psi, right? And then we have now rho sine theta, rho sine psi. We can distribute to this. So we have x is rho sine psi cos theta, and y is rho sine psi sine theta. Okay, careful writing the angle. And z is rho cosine psi. At least we got this, right? So this is the x, y, and z for the spherical. And also, aside from that, we also have the sphere equations. So from this, all of this, we can convert the xyz to the spherical. So this is called the spherical coordinates. Okay, now that's the conversions. Now, how to evaluate the triple integrals? How to evaluate the volume? So basically, to evaluate the volume, back to here. We already set uh, all the information for this rectangle here. So we can evaluate this as a delta volume in all axes, right? So I can write the volume as the delta volume so multiply all these sides. Okay, we have now these expressions. And we can take the integrations from the Riemann approach for the region E of triple variables for the functions. And let's say this is LMN. Let me write all the sum, and then this is from J. Okay. This is pretty much the same as we did in the previous sections. The key is this delta V. So all the cylindrical, spherical, they are all depends on what kind of conversion we need to take to change the delta V. So delta V is from here, okay, and going to put into our equations. So this will be the total will be limit, or maybe directly we can say this is the integral. Okay, the xyz we can change into our spherical coordinates. And then this will be d rho, d theta, and d psi. So this is the this is A, B, alpha, beta, and the psi, let's say C and D. Okay, now this is the triple integrals in the spherical coordinates. Okay, there's some how to prove, but I think I will skip that for now. So don't forget to write down this is the conversion, okay. This is if E this A, B, and then alpha, beta for theta, and C is for the angle psi. Okay, or you can also remember that because the one that are inside, like this one, it can be a functions of two variables, right? So it can be a functions of, it can be a function, let's say G2, theta and psi. This is also functions of theta and psi. Okay, so you have two angles as in the variables. So you treat the angles as the variables. Okay, before we are moving forward, let me just give you an example from here, maybe one example, and then I forgot to add some notes behind, but later I will take some sessions for that. So for example, evaluate. So you have this informations, and E is above the this and between spheres. So there will be two spheres. So first sphere is equal 1, and second sphere is equal 4. So you have two radius, right? So first, if you would like to at least draw the rough sketch, I think you can do that. And there is not really complicated function. So first is draw the region of E. I think we can draw the sphere. Sphere is, maybe this is the first. And maybe this is the second. Okay. And then it says it's above this z equal x squared plus y squared. If you remember, this is the cone, right? The cone. So I will make the cone. Okay. So it will be in between of this. So this is the cone. Okay. This is also cone, right? So the surface or the area of E is in between here. So between the sphere of the lower sphere is x squared plus y squared plus z squared equal 1. The upper is x squared plus y squared plus z squared equal 4. Okay, now let's set up what we know from this spheres. We know the radius, right? The first radius is 2, right? The second radius is 1. The lower is 1. So we can set up the row is between 1 and 2, right? And then for theta, because we can see that if we project this to the plane here, to the xy plane, it's just a circle, right? A full circle. So we can have the theta is also 2 pi, 0 to 2 pi, the full circle. Okay. Now the interesting part is the psi. Now psi is actually, if I'm drawing here, right? So psi is there. So we can take take the triangle, right? So you have this. You can set up with the with this cone. So set up with the lower surface, I think, and you will get that y over x is should be 1, right? So that your tangent psi is 1. So psi is actually pi over 4. And then you can write this in terms of psi is pi over 4. So you can set up triple integrals. And the one that you are going to evaluate is this, right? This is equal rho squared, and then square root become rho. So write rho, and write the conversion for spherical is rho squared sine. Don't forget that. And then the integrations, the differentials. So this will be pi over 2 pi 0, and then this is 2 and 1. And the integrations actually it's not that difficult. You can separate. You can look at this, right? This is rho. You can separate, and you can separate this into this. Oh wait, wrong. This into this, and this into this. And you can calculate. Okay. Okay, that's the example. So the idea, okay, for spherical coordinate is this rho squared sine psi. Don't forget this. Okay. And also how to convert x, y, and z. And you also have this, the sphere. So this is rho cos psi, rho sine psi cos theta, rho sine psi, rho cos psi. Okay, I need to go back a little bit to the triple integral because I forgot to tell you what's the one point that is really important in triple integrals. Oh, wait a second. Let me check here. Okay, after this. So actually in triple integrals, one application that really useful is the changing of order integrations. It's similar to what we did in the double integral, but it's a little bit complicated. I think if you can first you need to visualize the graph and visualize the boundary. This is really important. Imagine that. Remember that you have the double integral, right? And you can have set dy dx or dx dy, right? This will be a functions, right? Usually a functions. Depends on what you are going to observe. It can be function of x, can be function of y, right? But now, because it's triple integrals, we will have a triple. The one inside, it should be a function of two variables. It can be xy, or yz, or xz. The second part, the layer here, will be single variable. It can be x, y, or z. The last part is a constant. Okay, now we are setting usually dz, dx, dy, or dz, dy, dx, right? Because you are usually making z is a function of xy, or yeah, the surface, right? Usually. But then, can we make another reverse order? Like, can we change the order? Maybe dx, dy, dz, maybe dy, dz, dx, or any order that you want to have. And the answer, because we learned about the Fubini, right? The Fubini theorem, then we can also do the same thing here. Okay, let's say we have the questions to look at. Okay, let's say we have integrations. This is 0, 1, 0 x squared, 0 y. You have function of three variables inside. So in this case, the function here is not really important. The one that important is how you changing the order. If this is dz, dy, dx, can we write dx, dz, dy? Okay. And how, right? So first, let's look our boundary here. So this should be x, right? This should be y. And this should be z. Okay, let's start to draw and how we are going to make a conclusion. Okay, now you have the y equal x squared. It's practically here, right? And then x from 0 to 1, this is x, y, and z. So this is y equal x squared. And you will have, this is, let's say this is the x equal 1. This is 0. And then you have z equal y. Okay, z equal y. Z equal y is here. The line is here, but it will become a plane. So imagine this line is slicing up and making into this area here. Okay, let's say this is z equal y. The plane, it's cutting the axis, and then from this xy plane, imagine you need to connect this into here. So you need to take this going up here. Okay, so let's take that going up, and then you will have another a line there that is from the here, right? I hope you can imagine that. So this is actually in the front, and this should be dash. Okay, so okay, and maybe to make it better perspective, maybe I will erase this so that this is the front. Okay. Or maybe making a dash like that. It's actually not really shown that way. Okay. Okay. And now, from this figure, to set up our integrations become this too, we need to project. So we need to make a projections. So I will take here, make a projections. Projections. First is, of course, the XY plane. Okay. And let's say this is D1. And then make another projection. Let's say this is Z and Y. If you look at Z and Y, it's practically a triangle, right? So if you can imagine this shape here, you can rotate. Okay, you can rotate there, you can rotate there. You will see this is a triangle here, right? That is the ZY. Let's make another color. Say that's the triangle that you are going to see. So this is Z equal Y, and this is equal 1. This is D2. So this is based on this, and this is also 1, right? So this is correct. And another projections that you need is XZ. XZ is, if you look from here, from this XZ, from this side, you will see that it will have this. So imagine you are looking from here. So you will get imagine this is from that side. So this is Z, and this is X. And from what we know, actually, what we have learned from here, Z equal Y and Y equal X squared, we can actually confirm that this is actually Z equal X squared for the Z here. So this is Z equal X squared, right? And this will be D3. And this is also equal 1. Okay. Now, from all of these three, we can make conclusions for our setup. So first, we need to set up this. Okay, dx, dz, dy. So dx, dz, dy. So we need to start from y, right? Start from y at the last integrations, right? And it needs to be a constant. So we can set up the y from 0 to 1, right? So maybe we can write the boundary first. let's say the E is the boundary of our variables x, y, z. Start from 0 to 1 for y. And then we need to set up z. Z will be a single variable, right? Z will be a single variable, and we need to include z with y, right? And since z is equal y, and on this picture we can see that this is z, okay? So z is start from 0, and it's going up. It's going up into, if you look at from here, this triangle, z start from here, so it's need to be going up to z equal y, right? Until here. So 0, and then z, and then y, okay? And then lastly, the x. The x will be, if you look here, x is actually square root of z, and z is y, right? Z equal y here. So we can simplify this, becoming square root of y for x. So start from here actually. So start from x equal square root of z, and z is equal y. So x is equal square root of y. Or if you look here, this is the line, right? And it needs to be go through x-axis. So from here, it needs to go through up until 1. So this equation here, up until here, that will be the boundary for x. So square root of y, and then 1. So this is, I can write this in terms of 0, 1, 0, y, and then square root of y, and then 1, dx, dz, dy. Okay. Now, the second part, dy, dx, dz. Okay, now we start from dz as our constant, but since all is the same value 0 to 1, so we can set up easily for z is also 0 to 1, and next is x, right? So I need to have a relations between the x and z. So if we look at here, this is what we have done before, that x is also actually square root of z. We can use that in our equations here. So square root of z until 1. And then we need to evaluate z. We need to evaluate y. If we look from here, from y here, we want to evaluate y. This is our axis here. The upper boundary, of course, this one. And what is the lower boundary? Lower boundary will be the square root. Oh wait, oh here. The x squared, sorry. So we need to evaluate from here. Sorry, from this 0 here. But the 0 is actually our z equal y. It's approaching from there. And we are setting up until here. This is the upper boundary. So this is z and then x squared. And then this is 0, 1. It's a little bit confusing, but if you can determine with the picture, you can imagine, you look at the sides, you look at the projections, you will eventually understand the concept. And the idea behind all of this is still the same. This part here, the inside integration here, it should be related to the xy, okay? And this part should be about the it's x equal y, so it's a function of y. And here's a constant, the last one. Okay, but since the equation is just this equation, so this part you need to relate to, because it's x, then you need to relate this to z and y, right? And this part you need to relate to y, right? The function of y. And this is the constant. So, and for this one, it's y, so it should be related to x and z. That's why you have x squared and z, unless in the picture you can sense a constant like this one, right? Okay. Okay, I hope you get it. The additional notes. I think I will help you to understand this concept more on Thursday. We will maybe having another exercise, and I will upload all the solution for your exercise on the homework later on. And what else do we need to take? Okay, the last part. We'll going just for introduction for the last part. It's 15.9. So it's spherical. So sorry if I'm taking too fast for today, but you can actually review, and I will review on Thursday. Okay. 15.9. This is called the change of variables in multiple integrals. So what does it mean? Okay. So if you have let's say the functions xy axis, and then let's say you set up a region here, and you set up a point here. Let's say this is R, and then you have another axis, another rectangular axis, but it's not x and y. Let's just say this is v and u. And then we have another region here, it's S. And we have another setup for the coordinates. Let's say this is the coordinates. And then imagine that we can transform this coordinate into this, or you can transform S to R or R to S. Let's say from here to here is the T, and from here, from R to S is T inverse. And let T be the transformation from UV plane to XY plane. So TUV is XY. Okay. And then we can set up the X. So where X and Y are related to U and V. So X is function of UV and Y is also function of UV. Let's take G and H as the name of the functions. Or you can also write as this still okay, I think. Still understandable that this is actually mentioning that. Okay, so actually what we did is, remember that we have the we have x, y, and then we can convert to the polar, right? Remember that? So we have, for example, if this is the general equations, then we can convert this, become another, let's say in S region, and let's say this is becoming R theta, and you know, the dA become R dr d theta, right? You see that it has R here. This is actually what this T is about, and we will look for what is the general correlations to make up this T. Okay. And then because it has the transformation, it also has the inverse of the transformations, the T inverse. So if the x, y, we have this function of uv, then we also have u. Let's use another functions. This is function of xy, and v also has function of xy. So it has the T inverse. So if T is 1-to-1 transformation, then it has inverse. Okay, let me give you example on how we are going to do this and what is the relations. Okay, and then we can stop for now. So example, you have a plane x, y, and uv is defined by x is 1/4 u plus v, and y is half u minus v. So when you have t, this is xy. So when you have u and v, or sorry, this is u and v, you will have x, y is equal, you can plug in u and v. So 1 and 3, so it become 1. And 1 minus 3, it's minus 2, divided by 2, minus 1. So you can have this relations. And then the next one is, if you sketch the image, if it is bounded by 2, or maybe I will just directly go to the most important part. What are u and v in terms of x and y? So basically we can solve this. So first is x is 1 over 4 u plus v, and y is half u minus v. We can solve this by linear equations. It's not really that complicated. But let's try to solve this. And we have 2y u minus v. Okay, let's just subtract this. And then we have 4x minus 2y is 2v. And v is 2x minus y. And then do the same way and plus both of them, and u will be 2x plus y. And if you try to make the picture, you will see that it is transformed from this rectangle into this rectangle. Okay. Okay. So yeah, I will stop here for now. And please don't forget to fill in the survey. Okay. As soon as possible, I will announce the schedule for your final exam. But if you are not filling in the survey, I will not know your preferable schedule, and maybe if you have another final for other courses. Okay. I think we can stop here for now. And any questions? Example 15.7. Wait. Which one? This one? Okay, which one you want to ask? R, which are the first one? Oh, here. You mean the R, the equation R here, or R is equal square root of 3? The of square root of 3. Oh, from here. From here. So that is actually here, this square root of 3. You get it? So this will be square root of 3, right? Because we are only using this circle. But actually, if you want to look at in more, so if you want to look for here and here, I think that is, I think that depends on your sections area. Okay, I think that is, you can also use that from square to 3 to 2 if you have this, right? But you need to have 2, right? Like the r equal 2, and then the other r is square root of 3. Right. So I think both are correct if you look at the section, but careful to, so that's why I think important for the drawing the boundary. Okay, so you need to check the boundary so that you won't miss any small details, right? Okay. Okay. Any questions? If no questions, okay, again, don't forget to fill in the survey. I will announce as soon as possible for the final exam. But as far as I see your schedule, probably will have on Saturday, probably. Okay. Okay. If there's no questions, I will stop the recording, and I will continue the transformations. Okay, the last sections.